All right, what about concurrency? Well, Rust talks about fearless concurrency, and for those who've watched Dune, fear is the mind killer, and you will understand what that's about. And Rust is intended, of course, to make concurrency problems also compile time errors. That's actually really difficult. You can't get all of them. However, it is better, whichever ones that we can put at compile time, as I keep harping on about, to get them dealt with upfront as compile time errors because it is less expensive. It's difficult to do, but I think worth trying. Concurrency brings new kinds of problems that we've talked about in a previous concurrency course, the idea of race conditions, deadlock, etc. And they are risks that we generally are willing to accept because the benefit is your program can be faster. But faster is not necessarily better if it makes your program incorrect or make your program fail to produce an answer some of the time. Now, a student in a previous term told me that the Dune reference was too obscure, so perhaps this is more your speed. Okay, fearless concurrency, however you prefer it, is important in Rust. So yeah, if the compiler can help in making sure your concurrent program is correct, it doesn't directly make your program faster. However, if you can be more sure of the correctness of your code, and obviously you can never be completely certain, and correctness is elusive in the best of times, you don't have to spend as much time testing it before you can deploy it and move on to the next thing. And as we've already discussed, you can also save on some development time where you don't have to perhaps run under Valgrind to determine are there race conditions or are there memory leaks or other such issues. And preventing a bug from being introduced is faster than finding it and fixing it. And this ideally helps you to write business-critical code with confidence. Particularly if the thing that you're working on is really, really critical to the company that you work for. Anything that adds to your confidence that no bug has been introduced here or no unexpected behavior will occur is a good thing, and you probably want that. I mean, I wouldn't turn it down. It's valuable. Okay, so let's talk about threads. Rust uses threads for concurrency with a model that resembles the create-join semantics of the pthread. If you're unfamiliar with pthreads, perhaps you were a mechatronics student or in a different program, the course repository has a PDF refresher on that topic, pthreads.pdf. The background material will provide context. It is in C, so it's not in Rust, but for students who've taken a concurrency course in ECE, you would have learned about pthreads, so this would put you on even footing, so to speak, if you catch up and get an introduction and an understanding of the model. Of course, if that's all totally new to you and you've never written anything with threads before, it's something you should practice, and there's no reason why you should practice the C version if you're going to use them in this course. You can practice the Rust version, but to give you a catch-up on the basics of threads, that PDF is still worth reading. Okay, so you want to create a thread. All right, here's a way that we can do it. The mechanism for doing so is referred to in Rust as spawning. And again, this resembles the pthread create kind of semantics. But there's a couple of things worth noting. So up at the top, we have in our include directives, include the thread as well as a standard time duration include. And we're going to create a thread as the very first thing we do in main, where we say let handle equals thread, and then the function spawn, and then a couple of vertical bars, and then some curly braces enclosing the content of this thread. And the content of the thread is a for loop that says for I equals from 1 to 10. Print high number, and then I is substituted here in string from the spawn thread, and then we sleep for 1 millisecond. And then that curly brace and the closing bracket and the semicolon ends the spawning of the thread. And the return value of creating the thread is a handle. So we'll come back to what the handle does in a minute. We have a for loop in main where it says hello from the main thread, and then we sleep for a bit. And then we've got last thing here at the end, handle join unwrap. All right. There's a lot to work through here before we take this code and work with it, but let's get started. So when we create a new thread, we spawn it, and it takes as its argument a closure. A closure is an anonymous function that can capture some bits of its environment. That is, of course, an informal definition and not super precise, but it gets the job done in explaining what's going on. So we'll actually see as we do some later examples the thing about capturing some of its environment, and that variables that are declared outside of the thread can move into it, and they are, we say, captured by the closure. But in any case, we specify thread spawn, this is what I want you to run, okay, and that's specified using this closure syntax. The return value is a join handle, and a join handle is used later to join the thread. If you don't remember what joining is about, it is where you wait for the executing thread to be finished, and so later after main has run its for loop, this join call says I want to wait for the thread to finish before I continue in the caller. So in main we don't continue onto any further statement until the thread that we've spawned is done. If the thread is already done by the time we get to join, then of course we don't wait at all. We can just collect its return value. Otherwise, that's pretty much it. Again, if join is weird, this is covered in the pthreads PDF, and I suggest you go take a look at that. So what we'll do for now is take this code and run it. Our brief program, which we've just seen in the slides, and it is pretty simple. We can run it in really any way we want. Running it on the command line will do just fine, and it will build the program if it needs building, and then it will execute it, and we'll see, as we expect, high number one from the main thread and spawn thread, and those will be interleaved in some way, and we won't in fact exit until after that join has occurred. So let's add and see what actually happens if we have to wait for the spawned thread, and then we can try to run it again. Okay, well, I forgot a semicolon, so that happened, and can also run it using the IDE, and we'll see, hello from the main thread, and when the main thread is finished, it will wait for the spawn thread, and of course, after that has happened, we're good, and we do in fact wait for the spawn thread, and then we get the printout main thread is finished, as well as the spawned one. So, yep, everything went as expected. There's only one problem with this example, and that is it is way too easy. No data has been passed around from one thread to another, so this is too simple. It is not actually showing us any of the real-world use cases that we would expect to see when we work with threads, so we're going to have to improve our example a little bit. So if we actually want to pass data from one thread to another, there are three things we need to consider: capturing, message passing, and shared state. We will start off with the idea of capturing, and it calls back to what we just talked about a few moments ago about the idea that a closure captures some of its environment. So here is some code that is using the capturing mechanism for moving some data, passing some data from one thread to another. The only problem with this is this example doesn't work. And we'll actually take it for a spin, and we'll see what happens. However, the problem is that the lifetime of vector v in the thread might outlive the scope creating the thread. Well, okay, what does that actually mean? What happens here? See, when we are creating a thread in Rust, we're not really sure necessarily how long it's going to live. And so the compiler, being somewhat erring on the side of caution, will say, well, listen, that thread could long outlive the one that created vector v, and I'm not entirely comfortable with that idea because then we might have a borrow that outlives the underlying object. So that's not cool. We don't want that. So what if I put something after join that uses vector v? The compiler should figure out that v has to remain in existence until after the thread in question. But that doesn't work either. It says the thread might outlive the borrowed value once again. And again, we are saying that this doesn't work. And what's really the solution is to have a better understanding of what's going on with lifetimes in Rust. And if I try to actually run this code, we'll see what actually happens here. And we get an error that says closure may outlive the current function, but it borrows v, which is owned by the current function. And so the compiler, in its helpful way, says this is where the closure is created that may outlive the value v. V is borrowed because it detects that inside that closure, v is used in some way. And the function requires the argument to outlive static. In any case, the suggestion here to force the closure to take ownership of v, use the move keyword, and it suggests changing line 5 to look like this. That's actually going to help us, and that's something that we will want. If we do something like this, where we try to force it to acknowledge that v could outlive the closure because it's used after the join, again, doesn't work. We end up with the same problem. So what we should actually do is take the compiler's suggestion, and we should use move semantics to say, all right, what I actually want to do is transfer ownership of v so that it leaves from here and enters into the closure, and it belongs to the closure and can live as long as is necessary. So there we go. We have a vector, and we printed it, and everything works. Now, of course, if we want to use v again, we do a move, and it moves into the closure, so we can't use it here because, well, it's already been moved. So that doesn't work. If we want to get some data out of this thread, then we have to return it as an outcome from it. So let's try that. Okay, this does work. Why? Well, join, as we will have previously seen with pthread join, does allow you to collect a return value if there is one. The previous version did not have a return value, so we didn't care. It wasn't used for anything. But now we can assign the return value here of join. And this also provides an opportunity, if I take away the unwrap thing here, we'll see that this returns a result. And result is of type vector i32, so it contains an i32 if everything went well. Problem in returning will occur if something went wrong. I don't expect anything would happen there, but expect will unpack it and add additional information if something has not worked as expected. But basically, because join could go wrong for some reason, we are forced to handle that possibility, and you could use unwrap or expect in this situation. And doing so allows us to return the value out of the thread if one is needed. As we've seen previously, you could return the value if you want it back. If you don't need it back, don't do so, then just let vector v be dropped at the end of the thread, as would otherwise happen if we weren't returning its value. Now, one thing that I want to warn you away from is if the error message looks like it says something about making a lifetime of your vector static, don't do it. We'll talk about why when we get into the concept of runtime, of lifetimes in some more detail. And it's important not to get tricked because you will just go down the wrong path, and there even exists an issue in the Rust language issue tracker that says basically this is misleading for new people and maybe we should change it. Perhaps by the time you see this video that's already happened, but at least not as of the time I last looked. Okay, so a closure is kind of one-way communication. You know, we can return something out of it, but maybe we want something a little more formal and isn't necessarily between a thread being created and the context that is creating it. So we're going to do so using message passing. Message passing should hopefully be familiar to you from previous courses. You will have probably learned about it in some context, whether it is network communication, whether it is using pipes, whether it is using some interprocess communication mechanism other than that, message queue, something like that. And the idea, of course, is that you create a message and you send it over to the other party, the receiver, in that way. This strategy is very well structured and is generally safer than shared memory because it's harder to have race conditions or access memory that you're not supposed to access. And as the Joker says, it's not about sharing memory, it's about sending a message. So that's what we want to do when we get our choice. Now, the ownership mechanic of message passing is similar to that of postal mail, in that when you write a physical letter and you mail it to somebody, you relinquish your ownership of that letter when it goes in the mailbox, and when it is delivered to the recipient takes ownership of that letter and then can do with it as they wish. And we see similar behavior in Rust. One thread will create a message. It is the owner of that message while it's in its possession. It gives it over to a delivery service. Our delivery service here is the channel, and when the receiver collects it from that service, the receiver becomes the owner and can do with it as they see fit. So if we want to have two threads communicate, the Rust metaphor for this is called the channel, and it has a transmit end and a receive end. You will perhaps see a couple of similarities to this from other courses and other forms of interprocess communication. So let's make one. Let's do it. So your standard model is multiple producer, single consumer. And that is to say that you can have many senders on the transmit end, but only one consumer on the receive end. And this allows, just by default, if lots of threads want to send work for processing to a processing thread, then everybody wants to send work can have their own copy of the transmit end, but they're all received in a single place, so single consumer, and they are then consumed by the thread that actually does the work. I'm, again, operating on the assumption that you've, in a previous course, covered the producer-consumer problem, and you've even extended that to have the idea of multiple producers and multiple consumers. Okay. So if you want to create such a thing, you add the standard includes the MPSC, multiple producer, single consumer. That's why it's called that. And you create a new one using the channel function. And the channel function actually returns two values. It returns the transmit end and the receive end, and they're returned as a tuple, however you want to say it. And they are, in this case, the transmit end and the receive end. You can call them whatever you want, but we've called them TX and RX in this scenario. And so when we create a thread, we're going to use move semantics, which will then take whatever variables from the main function and transfer ownership into this closure as is necessary. Scanning over it, the only one is the tx value that we have declared. And so the transmit end gets moved in there. And we will declare a string says hi, and we will send it using the transmit end, and it does return a result. We'll just assume everything is fine and unwrap. If something goes wrong, an error will be observed here. If we left off the unwrap, well, an error might occur, but it wouldn't be reported because there would be no panic that takes place as a result of this. So adding the unwrap here makes it, well, if something goes wrong, panic, so that we would at least observe that something has happened. And then the receive end does exactly what you expect. You call the receive function and unwrap again to unpack the result and take what we got out of it. In this case, it will be a string. And we will then print saying got and then receive. So we'll print got hi as we would expect. Receive is a blocking call. So if the receive stuff runs before the send takes place, the main function is blocked, awaiting some data. And there is a corresponding try receive function, which would be non-blocking, so that if you want to receive, but there's nothing to receive right now, there's no problem, you're not held up, you can continue execution. We will cover non-blocking I/O. If you haven't already talked about it in a previous course, that's okay. You can just use the blocking version, and we will return to non-blocking I/O in just a little bit. So to have multiple transmitting ends, you need to use clone on the transmitter, and then you just hand those out as needed. So we could have lots and lots of different threads sending data. You just clone the transmitter end, and there you have it. As an important technical note, the type that you want to send via the channel has to implement the trait that is titled send. Almost all basic types in Rust have this trait. You can think of traits as being a lot like interfaces in other object-oriented languages. And almost all the basic types possess it. Any programmer type that is composed entirely of types that have the send trait automatically has the send trait. And you can explicitly implement it if you need. But we should actually talk about what are traits, because this is important and we've got to invest a little bit of time in that area. So traits work really a lot like interfaces. You specify a set of function signatures when you are defining the trait, and then for a type to implement that trait, it must provide an implementation for all of the functions that are defined in the trait. So if we make the trait here final grade, and there is a calculation here that returns a value f32, so a floating point number 32 bits, calculates your final grade, so with decimals, fine. And then if you want to implement that trait, you use an implementation block. It's denoted with the impl keyword at the beginning, and you say, I'm implementing here in this block the trait final grade for, and then the type that we are implementing it for. In this case, I've called it enrolled student. And you could imagine for this scenario, an enrolled student is saying, for a particular student in a particular course. So this student is student ID redacted, and the course they're taking is ECE 459, and then the implementation here will calculate the average according to syllabus rules. You should be familiar with those, of course, and in courses that you take, you probably are. So that's a very simple trait, and that makes it relatively easy to see how a trait is created and implemented. There's a couple of notes about traits. Number one, you can only define traits for your own types and not on an external one, like not on those that from another package, so you can't break somebody else's code. This is ever so slightly a problem, as we'll see later on when we talk about GPU computation, that I want to implement a trait on a particular type, but I can't, so I have a little workaround, which is not ideal. Again, at the time of recording this, that has not been addressed. If I find some time later, I've been invited to contribute a patch to the project, so this doesn't happen. But again, I have to find the time to actually do it, and it is in somewhat short supply. So you can only define traits on your own type. So if you're importing something from, or you have a use statement, and you want to define a trait on it, you can't, because it's not your type, you don't own it, and you can't break it. The second thing is you can create a default implementation for a trait. When you are defining the trait, you can say, look, unless you override it, here is how final grade is calculated, and that is fine. And also, traits can be used as a return type or a method parameter, so you can say this function returns something that implements the final grade trait. Could be whatever it is, doesn't matter. Whether it is an enrolled student, whether it is a course registration, whether it is a widget, as long as it implements the trait, it can be returned, and you can say the same for an incoming parameter. If you had a function that says calculate term average, it takes 5 objects that implement the final grade trait. That's all you really need. You don't care what their underlying types are. And if you want a parameter to be more than one trait, so it has to be both final grade and serializable, let's say, then you can use the plus symbol. So you say this variable x is of type final grade plus serializable. Neat. When you need a parameter to be a couple of things, that's kind of cool. There are 3 traits that are actually important to us right now that we are interested in spending some time on. And they are iterator, send, and sync. Iterator is the easiest one to explain. You put it on a collection, and it allows you to iterate over that collection. So you have a list, you have a set, something like that. If that collection implements the iterator trait, it means that there is a standard way for iterating over it, and using the iterator approach is sometimes more efficient than a for loop construction, because it lets the compiler skip over bounds checking and stuff like that. So a lot of the standard collections that we'll use implement the iterator trait, and of course you can just use it, the iterator. About send. Send is used to transfer ownership between threads, so it's a way of saying it is okay if you do this. This is usually the default, but some Rust types very specifically choose not to implement it as their way of telling you, please don't pass this between threads. If you are looking at something like that and the compiler says, no, it doesn't implement send, it's a hint that you need to use a different type. We'll see that in the next lecture, that if we use the wrong kind of reference, the compiler will say, I don't think you should do this because this is not a good idea. And because of the rule that says we can't implement the send trait on something that we don't own, obviously we can't just say, oh, I'm going to fix that by implementing send. That wouldn't work, doesn't do what we expect, and therefore we're discouraged from doing the wrong thing just to make the compiler quiet. So if the type that you are encountering does not implement send, there probably exists an alternative which does do what you want, and you should look for that. If you are making your own type and it is inherently not safe to send, and you want to implement it yourself, you may. You just have to guarantee the thread-safe transfer of ownership yourself. It's not a good idea if you can at all avoid it. And then there is sync. And sync means that a type is thread-safe, and that means it could be referenced from multiple threads without an issue. And this is the default for primitive types as well as programmer-defined types that are composed entirely of sync types. But that doesn't mean that all operations on a sync type are safe and no race conditions are possible. It just means references to a type can be in different threads concurrently, and you can't have multiple mutable references. Actually, if you want to be able to modify the value, something that's shared between threads, then we need a mutual exclusion construct of some sort. And so, yeah, there does exist the ability to use a mutex, and you should, I hope, be familiar with the idea of mutex from a previous course. The idea of putting some sort of synchronization around accesses to a shared data type. And although message passing is recommended, you may have a valid reason why you don't want to use it, and you want to use a mutex, that is to say shared memory, instead. Performance is a valid reason if it's borne out by your testing or your data, and this does exist in Rust, and I'm going to go on the basis that you know how they work, so I'm going to skip the part where I make some analogy involving coffee shops and locked doors, because you should be familiar with it. What is different about the mutex in Rust is that the mutex wraps a particular type, so it's defined as a mutex and then in angle brackets a generic T, so you fill in. So if you want it as an integer, it'll be a mutex that is associated with a 32-bit integer. And what is important and what is good about this is that the mutex always travels with the value it is protecting. They come together as a package, making it much more obvious what mutex goes with what data, and making it so that you always have to have the mutex to access the data. In a C program, you are supposed to lock the account mutex before modifying an account, but you could just not. There's no like programming language level compiler error that says, hey, wait a minute, you forgot to acquire the mutex, and stops you from accessing it. This is solved by the idea of packaging these things together, as we see in Rust, where to access the data that's in the mutex, you have to acquire the lock, and that makes sure that the data is always protected in that regard. So here's a simple example of using a mutex. We'll create a mutex using mutex new, and the data we're going to put in there is an integer value 5. When we want to acquire the mutex, we call lock and then unwrap, because we're assuming that everything went well, and throw a panic if we did not. And it returns you a reference. In this case, we want it to be mutable, so we're going to say let mute num is assigned m.lock.unwrap. And then using this mutable reference, we will change the value of num to be 6. Okay, very good. That does what we expect. And we've used manual scoping here. Why? Okay, when we lock the mutex, the thing that we are actually working with is a mutex guard. So the type of num in this block is actually mutex guard, and it is our possession of the lock. When that possession ends, that is to say that the mutex guard goes out of scope, as it does when we get to the end of the manual scoping curly braces, it means that the lock is released. So not at the end of the function, not at the end of this iteration of the loop, anything like that. That's pretty good. It eliminates a lot of the, oh no, I forgot to unlock scenarios that could also occur, as before. Just as there's nothing that stops you from failing to lock a mutex, you can also forget to unlock a mutex and really give yourself a headache. Whereas in this case, using the mutex guard, when it goes out of scope, the lock is unlocked, and everything is done automatically. You don't have to remember to do that if you don't want to. Okay. Now, the use of the mutex in this program is very silly. It introduces the mutex syntax. It allows me to talk about the mutex guard. But this program has only one thread, and the mutex doesn't really do anything. If we want to use it in multiple threads, well, we need multiple threads to have access to that mutex. We can't, unfortunately, just say that references will do. You can't really have references to this mutex because the mutex has to outlive all of the other threads, and the compiler will suggest moving it into a thread as we create it. But that doesn't work because we can't move the same mutex into more than one thread because it violates our rule about having only one owner. And cloning it doesn't help because that makes another copy of what we've got and isn't a mutex protecting the same thing. So what do we do now? We're going to have to break a rule. We need the ability to have shared ownership of some memory. We don't know how to do that yet. We're going to learn about that in the next lecture, and we'll find, actually, when we start breaking rules, we might like it, and we might want to break more than one. So we're going to have to be careful knowing what rules to break and which ones not to break, but we do have to, in some circumstances, break some rules to get the program to do what we want. So we'll learn about how to do that in the next lecture.